entity is using each day. Hopefully it's a daily load. And from that number that we determine, we then go forth and select the size of the system and how big it can be, and the distribution design for that, for the specific building or unit.
Thank you so much. So basically, this is going to be the main topic of the presentation. Before we move on with the rest of the slides, I just needed to point out a couple of things. First thing first, for everybody who's participating for this presentation today, please note that we will be recording this session for basically future training purposes. We might use it on our YouTube channel, stuff like that. So just please take note of that. And then if you have any questions during the presentation, please just feel free to type it in the chat section. I set aside a time for us to go over all the questions that we might get and try to get to as many as we can. And the ones that will take longer, we'll definitely get back to you with all the information that you need and make sure that no question will go unanswered. So this is going to be the general agenda for our presentation today. We're going to look at the loads for different types of application. We're going to start with residential applications. We know that there are a lot of new energy codes, energy regulations coming in, focusing on residential applications, different types, going single family all the way to large multifamily installations and construction project that will require solar thermal in one shape or another. So we're going to touch on those. We're going to look at commercial applications, and at the end we're going to go over the industrial process heat applications, and basically give you the preliminary introduction to how to determine the load and how to translate that information, that load number, that energy load that you have for the heat that you need, basically, whether it's a domestic hot water load or other type of heat load that you need, and how to calculate that, and then how to translate that to the size and the type of the system that you will need, basically. So, we talk about the applications that we have, having residential applications or industrial applications. Regardless, we always start with, figuring out the load. And the easiest type, to determine the load is how many gallons of hot water, because we are talking about solar water heating systems here. So let's determine how many gallons of hot water do we need, what temperature do we need that load at, and what temperature are we getting our cold water at.
We'll also cover load profiles, which is a fancy name. When you use the hot water and how much, that's a load profile. Is all the water used like within the first hour of the day? Is it used during the entire day? Is it used at night? So we'll cover that a little bit also.
Definitely. We're going to talk about solar fractions briefly. Then we're talking about residential applications. Going to look to basically size the system for single-family residential applications. We're going to size the system basically to meet 90% of the annual energy load for the building. When we're looking at larger commercial applications, we are usually aiming for about 70% solar fraction, or basically the percentage of energy that will come from the solar thermal water heating system compared to the entire energy demand. As this is a very general rule of thumb number, as Bob was just saying, there are load profiles that will come into play. There are going to be many different factors that will come to play that will dictate that number and what can be done. There are going to be different project constraints such as space available. I'm going to get into all those, but this was a very general number that we're looking at. So this is basically a visual representation of what do we mean by solar fraction. So if there's always for solar water heating system, there's always a backup, there's always an auxiliary unit. And Bob could get into a little bit more detail about like the necessity of an auxiliary unit and how that backup unit is actually sized.
Well, the backup unit, which you see in the PowerPoint, it's 10% primary. That means 10% of the total energy used during the year in this particular example would be contributed by the primary. Why you need the primary? 10% of the time it might be cloudy, overcast, you might have relatives over, friends. You might decide you want to use more hot water than the solar can provide at that specific moment. The primary must, by code, provide all the hot water that the residence or structure needs at any time. So you cannot, with the primary water heater, you cannot downsize it generally. It has to be sized for the building. So if it's a 2-bedroom, it might be small, 4-bedroom residential, a little larger, and then commercial, obviously the variables are so high. The primary is always sized to cover people if there's an increase in census in the building. So never downsize that primary, but the solar is contributing by means of preheating the water. In this example, 90% of the energy that would be used for heating hot water.
So here is an example of solar fraction for a commercial application. As you can see, the system is larger, is the commercial application kind of a system, and the solar fraction that you're aiming for in this scenario is 70%. So again, as Bob said, that water heater that's designed to do 30% is actually sized to be able to do 100% of the demand, but we try our best with the solar thermal system to design it in a manner that the primary heater won't come on more than 30%, for example, in this case. But it's very important to keep in mind that no matter how much solar you want to add, you should never basically sacrifice your primary water heater. That system should be able to meet your energy demand for that specific application. For solar fraction, how we come about it is different. The required solar fraction is a lot of time communicated to us by the energy engineer, the energy designer for the building. They already went through the calculations that they needed to do based on many different factors, such as like insulation factor. So they let us know that's a specific solar fraction. In some cases, if there's a specific energy code, such as Title 24, then they're trying to meet. Here in California, that's the energy code that we follow. Basically, for that, if they're trying to follow the prescriptive method, it will tell them that, okay, if you're in this certain climate zone and this is your application, this is the solar fraction that you're looking for. For instance, if you're in zone 1 to 9 in California, for a multifamily residential building, you're looking at 0.2 or 20% solar fraction. In cases there are energy certifications that you're looking for, such as LEED. In those cases, again, based on the solar fraction that you can achieve, there are certain LEED points that comes with it. For example, if you're going for 40% solar fraction, you will be able to get 2 LEED points, and then 60% solar fraction will get 3 LEED points. Important note on LEED certification, which is something that a lot of buildings are now going after, and by U.S. Green Building Council, it really it is a meaningful certification for the building. It really goes into the detail of how much energy that building is actually saving and how close it's getting to be an actual net zero building. And one thing that I've noticed in most LEED projects that I've seen so far, whenever there is the desire to achieve LEED Platinum level of certification for the building, there's always a solar thermal system designed and sized to maximize the LEED point gains possible. There are local jurisdiction requirements. Bob definitely knows more about like different areas that have different solar fraction requirement for installation. So,
right. The local requirements are based on their different geographic area and their energy profile, total state energy profile. In particular is Hawaii. They've had energy standards for an awful long time. They've had mandated solar fractions in the 0.9 to 1.1 range, which what they're trying to do is offset any load, duct loads that the utilities are talking about in the evening when the electric rates go up, or the electric usage, pardon me, goes up. They want to minimize the electric water heaters that are in Hawaii from all turning on at once and causing the grid to, strain a little bit more than it should. So that's in Hawaii. That is the primary reason to have the solar fraction so high. In Puerto Rico, kind of the same reason. They want to minimize the amount of electricity used on the grid during peak times. So that's why they have such a high solar fraction. We want to have mostly solar hot water for their particular area. Nevada has an 80% solar fraction. Again, they want to try to offset that electric. A lot of times it's an electrical load on the grid they want to shed. They want to minimize any peaks. So there might be community electric grids that may have their own programs, and you just consult with them, talk to the utilities or who's ever providing the fuel source for your water heating for any specifics.
One thing that's definitely worth mentioning now that we're talking about different solar fraction demands by different jurisdiction, and we know the movement that we are seeing with moving towards like complete electrification of all the new buildings, new construction, moving away from natural gases, and moving away more and more from fossil fuel and going toward 100% electrification. Keep in mind that when we're talking about solar domestic water heating, domestic water heating in general accounts for anything between 27% to 42% of the entire building's energy demand, depending on the building type. So for a single-family residential, dualing is about 30%. And interestingly enough, when we go to multifamily residential buildings, that can go all the way to 42% for basically the percentage of energy usage that was going toward water heating. So we will see the importance of an effective solution to kind of address that load that will come onto the electrical grid the more we move toward electrification. If you have all electric water heating for all your buildings around 5 o'clock, 6 o'clock in the afternoon, when everybody comes back from work and they want to get take a shower, start getting dinner ready, kind of wind down from their day, you will have an energy surge that will go through the roof. On top of that, you will have this hot water demand that will also surging. So if you're not addressing that issue with an effective solution such as solar thermal, which is displacing that energy with solar energy, not with another type of fossil fuel energy converted into electricity, is actually replacing it with a renewable energy source and is taking that load off the building. That's why in areas that they have more electrification and less fossil fuels, the more expensive the fuel gets, there will be always a higher demand for a higher solar fraction because it's easier to justify. So we're gonna go into the loads and how to calculate the loads for residential buildings. We're gonna start with single-family residential buildings, and then we're gonna work our way up. Basically, it's a straightforward method for single-family based on the ASHRAE standards that we've seen, and also different handbooks that are available for solar thermal programs, incentive programs. There are established methods for basically both new construction and retrofit. For new construction, when the number of occupants is unknown, the gallon per day consumption of hot water is determined by the number of bedrooms. So they start off with 20 gallons per day for the first bedroom, 15 gallons per day for second bedroom, and 10 gallons per day for each additional bedroom from there. And for retrofit, they do it based off the number of occupants, 20 gallons for the first occupant, 15 gallons for the second occupant, 10 gallons per occupant from there on, and so on and so forth. But Bob will definitely tell you that, yes, that's what you use as the guide, but if somebody is actually designing something, there's always safety factors that you want to include into your oversizing factors.
Some of the factors in new construction, one of the big ones is if they have a large tub, a jacuzzi tub that they fill and dump every day, that really adds to these numbers. If they have a rain shower that has 5 heads that they run for 20 minutes, that can change the dynamic of this. On new construction, that's so you can compensate for that because you know what's going in. In a retrofit, same thing could be possible. They have a jacuzzi tub. A lot of times with retrofit, now you're talking about occupants. Who's there? Do you have 5 teenagers there? That can change this instead of 10 gallons a day per person to 15 or 20. So you have to look at on a retrofit, you look at the specific home or resident, as we're talking single family. On new construction, you have to look at what appliances, fixtures they're putting in. Bedrooms is a start, but if they, like I say, if they have these high hot water usage fixtures, you have to up the number to compensate for that.
Exactly. So just like any other, the type of calculation, the more data we have at the beginning as input, the better, more accurate outcome we'll have at the end. So yes, these are just general rule of thumb methods that we use in case there is no other information available to us. This is, yes, a solid way to go about it, but as much more information at the beginning, the more accurate of a result we'll have for sizing of the system. When it comes to multi-family building, now it's a little bit different. And we start off with the most accurate method of establishing the energy demand, basically, and that would be by doing on-site monitoring. So, Bob, could you elaborate a little bit in detail about the importance and how to deploy those systems? What are the best ways? And we get into, we'll have a dedicated slide for it, so if you want to go over it briefly, and then we'll go over the detail later on.
On-site monitoring essentially means we are measuring the amount of water that is entering the water heating system, and that is how much hot water that's going to be heated and then eventually fixtures. So that's the daily hot water usage, as opposed to in more detailed designs if you have daily hot water gas used to heat hot water in total. That's a little different. This is just the hot water used, how much water we're pushing through the system, and then we measure how hot the water is coming on the discharge side and the cold water ambient coming in, and from there we can get a accurate measurement of what it'll take for the sun to do whatever percentage you want.
Definitely, we're going to talk about this topic a little bit more.
Yeah,
and then there are industry established standards that we can use, such as ASHRAE standards. We're going to look at those for sure. And there is another method that is basically fuel metering that we're going to use at the fuel consumed by the specific water heating unit that's on that building. So we're going to talk again, ask Bob's opinion and his recommendation for on-site monitoring in a little bit more detail about what we will look at, how long should it be for, and what are some of the key factors that should, be,
On-site monitoring, the simplest way is the most less intrusive is an ultrasonic flow meter. That will be installed according to its manual onto the pipe that leads to the supply pipe to the water heater. And also you can put hot and cold sensor on it so you get those readings also. Excuse me, you want a minimum of 14 days if possible of monitoring to get an accurate representation of what's being used. The longer the monitoring period, the more accurate the data. There's simple water meters, cold water meters that you can put on. They won't give you temperatures, but you can estimate the temperature if you want to go that route on the inlet and the outlet. And then cold water meter can be installed. Now that's intrusive. Plumber has to come in, put it in. and then that gives you a reading. What I found, and some of them have data loggers, so you almost need, with the ultrasonic, they're usually built in, so you can download the information from a chip that's in the meter. Standard dial water meters don't have that option generally. They're old style, very accurate though. They're revenue grade. You just have to read the meter at the beginning and at the end of the test and do the numbers from there. We find that a lot of engineering companies are doing this now, architectural companies on projects, and in the end, the owners or the engineering companies or architects leave the meters in place for the owners. So that's so they can have an accurate reading of how much hot water they use. They can look at it if there's a change at the building for some reason. They added on, a restaurant on a multifamily. They added on a wing, or they've had an increase in census. So they can. It's kind of like having an electric meter now on on that specific load.
And Bob, as far as duration of the monitoring, what would be?
Duration, well, at least 2 weeks.
Mm-hmm.
Some can go longer if you want to. The longer period you have, the better profile you. I mean, what you get is a net, gallons. During that period, you divide it by the number of days, you get gallons per day. Some of the more sophisticated metering will give you a load profile, which ties that hot water use to time. So you'll have a curve. All the water in this case, you could see it used in the evening when everybody comes home. You could see a use, especially multifamily, in the morning. A lot of hot water there. You use it in the morning all day, nothing happens. Not now, but in the past, everybody's been at work or doing something else. And then in the evening. So those load profiles can help. How do they help? Well, if you need hot water in the morning, where is it coming from? The sun's not up yet. Well, you have a storage tank that we'll talk about later that has the capacity to deliver that water when it's needed in the morning. In the afternoon, hopefully the sun's heated the tank. It's a good day. It's heated the tank. It's ready to go in the evening. So those load profiles are very helpful for refined numbers and delivery of solar heated water to the property.
And Bob, do you want to go over some of the equipment that we might be able to use for both metering and also load profiles?
Yeah, the monitoring equipment's there's sensors, temperature sensors that will measure the cold inlet water, which usually doesn't vary too much in seasons, 4 seasons. It's usually good for the quarter, 4 quarters of the year. It might vary in the winter and the summer, but during those time periods, temperature doesn't change. The output usually doesn't change either, but that's what the sensors are for. It gives you the accurate numbers. So on temperature. The flow measuring devices are ultrasonic. They're usually plus or minus 1% accuracy. You have paddle wheel, which is a standard water meter that most people have residentially or even multifamily. They have a main master meter. They have vortex shedding, which is the Grundfos type that uses the velocity through the sensor to calculate flow. There's ultrasonic, which is there's a lot of them. They're small. Some of them are 1/2-inch size pipe to 2.5-inch, are like a range of mid-range cost units. They give you temperature in and out. They also have data logging for load profiles. Magnetic are similar to mostly for industrial applications. They'll give you large volumes of water that are being used for whatever you're monitoring. Then from there, all that information from the sensors and the meters go to a data logger or converter that holds it or transmits it, depending on. Most of them are kept within the equipment on site, and then somebody comes and retrieves a chip, an SD card, and downloads the equipment to get the information. Because sometimes they leave it on. You know, they'll have enough meters, they'll leave it on longer than 14 days, but they need 14 days to get the ball rolling, to get the sizing done, to make a presentation to the owner or to the architects. And they'll leave it on longer if they can, so they can get it. If there's any variations, they pick it up. So that's the data loggers. And some, not all, but some will allow for transmission over the internet. You can hook up a LAN Ethernet cable and download the information there. Those are like on the high end of this equipment.
Awesome. So that was the best, most accurate way of establishing the load, which was on-site monitoring. In absence of that, we can use standards, industry established standard, basically. The most well-known standard in our industry, ASHRAE, basically has a chart for determining the daily hot water consumption for different type of application. As you can see, here's an example. This example that you see, the chart that you see here, is a combination of ASHRAE and also the standard feedback that we basically receive from our contractors in the field, from the sizing that we have done for different projects. We basically put those information together and came up with this to establish a daily hot water consumption. You can definitely use the ASHRAE standard by itself as well. Very accurate. You can find that information in most incentive guidebooks. They include that information, especially for commercial incentives. They always include some sort of method to determine the daily hot water consumption. As you can see on this example, it tells you if, for example, you're designing an apartment building that has double bedroom units, you will use 35 gallon per day per unit to establish the load for them. In case you're designing a hospitality or like a hotel application kind of a building, if you're doing 20 units or less, you will assume 20 gallon per day per unit, and that will give you the daily hot water demand. And from there, you can basically verify the information and go from there and establish your energy load for the day. Another way that you can establish how much energy you're consuming is by metering the fuel that's going into your water heater. Different water heaters have different fuel efficiency, so you will kind of need the information from the water heater, and you need to know exactly how much fuel that specific water heater uses. Doesn't matter, electric, gas, whatever it is, it needs to have a dedicated individual metering device installed on it. So from there, you can kind of establish the energy, the daily energy load that you have, correct, Bob?
Yeah, this slide will tell you how much actual fuel you're using and the natural gas, and the utility can supply you with all the content, energy rating of the gas they're supplying. And it could be propane also. You have the meter on there. That tells you all of it. That gives you the amount of gas used, and then, you know, if you combine this with a meter, you can see where your inefficiencies are, what's going up the flue there. If there's a recirculation line, this covers the energy that's used in a recirc unit. So that it defines the total amount, which is a little different than the daily hot water demand. This is what you're using to get the hot water hot. And so this is a very combination of all the items that we're talking about monitoring, plus this will give you a highly accurate means of determining what your energy uses is, and then going forward from that information, you can, in design, attack those loads differently. So you can offset those loads if necessary. So, example, if the recirc pump is using 20% of the gas, and you determine that through the flow meters, you can design the system a little larger and have a preheat in the loop to heat that. So there's all kinds of potential to lower the load, the total gas use, or electric if necessary. This is industrial applications. You can see the systems are usually we say they're unique and they have to be their project specified. They can be on the ground with footings that you see. They can be on roofs that are usually structural engineers, architects get involved with all this, and then the mechanicals can get involved with the distribution system. There could be a solar contractor specifically on it, that, which is nice to have, that can oversee the whole thing. But again, the limiting factor with industrial projects usually, because they use an awful lot of hot water, is the available real estate to put it on, whether it's rooftop or land. So that's something you have to look at, in the initial site visit or site summary that you review.
Yeah, absolutely, Bob. That's correct, because once you're looking at industrial applications, for example, different types of farms, both dairy farms and, for example, turkey farms, laundries, they use an incredible amount of hot water for different type of applications on a daily basis, and the limiting factor becomes, as Bob said, the real estate. Because if you are, for example, somewhere that real estate is not that expensive, yes, you can probably dedicate an acre of your real, property that you have for your solar thermal system and really see the benefits of it. For example, in North Carolina, I do believe we have a very large installation in a turkey farm that I think it's 1,000 collectors installed on about like 2 or 3 acres of land. And the interesting part is, as I was saying, the loads are so huge that even with that kind of an installation, with 1,000 collectors being on that farm, it only, I think, makes up for 30 or 35% of the entire energy consumption that they have. So as you can see, that will become the limiting factor. Another limiting factor would be the storage. If the application that you are going for will require some sort of storage, for example, if something that you have to do, for example, at the end of the shift, they want to do clean out with really hot water and they need 2,000 gallons of hot water ready at the end of the shift, you will need some sort of storage to basically accumulate that solar energy during the solar day, which is about like 9 a.m. to 3 p.m. Gather as much as energy that you can, store it in that storage, and then deploy it at 6 p.m. or 7 p.m. or whatever that end of the shift.
That's like the battery storage that's all in the news now. You want to store the electric, well, for this would be thermal energy. You want to store it in your solar tank battery. We call it that here, and then use it just after the sun goes down, if it's an evening shift, and they, like Amir mentioned, clean outs and clean up for the day, then you have it to do it. So that all that's in load profiling, which again, the more data we get, the more we know about the project, the more accurate we can do the design and help with that.
And again, as Bob was saying, load profiles matter a lot, because the other way around, in a laundry application that's operational 24 hours a day, they have a lot of demand. So it doesn't matter how much hot water you can create during the daytime, it will probably consume all of it. So you probably won't need as large as the storage. You'll probably use some sort of a storage buffer tank just to transfer that heat energy as fast as you can into your line and basically reduce the load on your boilers or whatever is the method of providing the primary heat, basically. Right. So understanding that load, how much is it, is one thing, and then how it acts, the profile of that load, is also important in order to design a system that's optimized, that is really benefiting the system owner, and it's basically designed to maximize the equipment to efficiency ratio. Once you know the daily hot water consumption, if you did the monitoring, if you use different type of methods to establish what's your daily hot water consumption, then there are a lot of good softwares out there that actually can convert that information. Once you have those numbers, you can convert that information into the size of the system that you basically will need and the tilt angle of the array that you will need. And you'll basically be able to simulate your system performance throughout the year based on the weather data, the solar irradiance data available for that location, the type of the application that you're looking at, whether it's like commercial pool heating, residential domestic water heating, multifamily, or industrial heating. The type of the collector, so these softwares, they use different data banks to basically have the efficiency performance of the collector, all the performance data of the collector. Basically, they use, for example, the OG100 certification data for each collector, and they plug it into the software calculation, and that's how they get the simulated result of the system's performance in that specific location. From there, you can basically size your system accordingly and be confident that you're getting the right system for the solar fraction that you need. Couple of examples of softwares that you used. Bob, if you want to elaborate on F-chart and both Polyson and F-chart a little bit, please.
The primary, one of the first programs for solar thermal was F-chart. It was developed by, I believe, University of Wisconsin and Madison. It's still in effect. It's very useful, very straightforward. If you look at it, this is on the screen, an active domestic water system, and all the data is plugged in to the right. The first thing it shows is Title 24. It's the zone, I'm sorry, the climate zone, and that's from California. You plug in all the data, and then at the bottom, you get the contribution of the solar. And the very last number in the lower right is the yearly contribution of 5.45 solar fraction. That's what the F stands for. So it's 54% of the energy for the hot water is contributed by the sun. Quickly, the columns are solar. That's the total solar available, January through December. The domestic hot water load, that's your total demand for hot water based on what you've plugged in as data. The auxiliary is what fossil fuel or auxiliary heat you're going to use during the year. And then again, the solar fraction is what the solar contribute. Polysun is another very good software. It has more data points. There's more system designs that can be run through Polysun and give you accurate simulations of what you're going to see. So we have both of those available to our engineers or designers or even our distributors. A lot of times things come through distribution and then we funnel it back through distribution and they funnel it to their architects that inquire. So a lot of times we don't even see the end users, but we help through our distributors or dealers.
So we're just going to quickly go over some of the common design for commercial systems that we'll see out there. This is an example of a pressurized direct system. As you can see, the city water goes directly through the collectors on the roof, gets heated, goes back into the solar storage tank. The solar storage tank is feeding the main water heater, basically. So this is a very common design they use in areas that they deploy direct systems, such as Hawaii. The commercial systems in Hawaii, they use this system widely. Caribbeans,
yeah, the direct systems are used, the primary plate where the water quality is good and there's no possibility of freeze. They're very efficient because there's no heat. The heat exchange is occurring in the panels only, and it's direct from there. So this is potable, usually potable water that's running through this entire system out to the fixtures.
We're going to go on to our indirect system. So as Bob was saying, every time you introduce a heat exchanger point or a point of changing basically heat exchange, you will lose some efficiency, but there are areas that you definitely need indirect system, glycol and drain back. So here are some examples of glycol systems. As you can see, the systems on the left side of the screen is with unpressurized storage tank. It's using a solar station XXL by SunEarth to operate both both potable side and the solar side of the system. This is again a preheating system for the main water heater. As you can see, is heating the water that's going into the main water heater, and on the other side you will see the same solar station XXL being used on a pressurized system in this case. And again, doing the same thing, basically the water. There are definitely different designs that can be deployed depending on the application, the project constraint, and basically with solar thermal, we always say there is no one golden key to solve all mystery. Basically, every project, especially when you're looking at commercial projects, yes, there are rule of thumb, yes, there are general designs that we recommend, but there are so many different solutions, and we can make sure that we'll find the right solution for that specific application, that specific building, so the system will be at its optimum level.
So on that, going back to that, just the two main differences. We have an unpressurized solar tank on the left, which is, they're usually Hydroflex, they're foldable, they'll go in a room, their cost is less. On the right is the pressurized ASME tank. And both projects are fine, just depends on what the building requires and design, what the architect or engineers are speccing.
Again, another very common design, especially commercial project, drain back design. There are many different benefits involved with using a drain back system, especially knowing that it will provide really, really good safety measure against both stagnation, overheat, and freezes. So depending on the type of application and where the system is being deployed, it's really important.
Yeah, what we found, just that overheat is the main benefit of drain back. And let's say you have a school that's operating spring, or fall, winter, and spring, and summer they're off, and you have a 100 panel job up there to handle all the hot water and other loads that you've calculated, and then there's no load. June 15th comes and everybody's gone. Dormitories are empty, whether it's college or high school or grade school. So you have, especially dorms, excuse me, you have no load, and you have a drain back system. That's okay. It'll heat the tank to the high limit to its setting, and then everything, the pumps shut off, and all the fluid drains out of the collector back into the tank. So the panels sit up there dry, which they're designed to do, and the fluid is back in a drain back reservoir or in a large tank. So drain back is very, I think it's seeing more and more use because you have these intermittent, again, design, the load profile is that you have to, if you don't monitor it, you have to look at the project. What does the school do in the summer? It goes away. I mean, the census drops, the load. We've had, anyway, that's for another day. We know from experience what happens when you have a huge solar system and no load. So drain back takes care of those concerns.
Bob was mentioning that in some cases they leave the monitoring systems behind even after the building is in operation, full occupancy level, and they can see the performance of the system. So it's really important sometimes to actually see what you're getting and what the system is actually doing. So here is a really good example of a system that was installed in Massachusetts. Basically, it uses a monitoring system called Thermal Grid, which provides really, really accurate live data of the performance of the system, different temperature reading, different pump performances, basically. So all that information is available. And this will show the system owner that what your solar thermal system is actually doing for them. In this specific case, once we went back and looked at the system performance data at about 4,200 hours before operation, we found out that the pump used about 112 terms of energy. Those were the ground force UPS 26150 pump. So even though they're pretty large pumps, you can see in 4,200 hours of operation, 3 pumps together only used about 112 terms. And that's why solar thermal has such a high efficiency, because pumps are really, really efficient in operation. And the system provided about 2,700 terms in solar thermal energy, basically. So you operated those pumps to send the heat transfer fluid to the collectors, collect the heat, and bring it back. And that operation resulted in 2,700 terms of energy. So when we put those two together, to calculate the COP, or the coefficients of performance of the system, which is basically how much energy you put into the system and how much energy you're getting out of it, the ratio between those two. You'll see that the COP of a solar thermal system in this case is about 24. We usually say the COP of a solar thermal system is about 9 to 12. In this case, it's 24. It's incredibly high. And just to put that in perspective for you, a solar, for example, a very efficient heat pump water heating unit operates at a COP of about 3 to 5, depending on the manufacturer and whatnot.
So the other thing you can do with this is, if you see our blue TRB collectors, if an ad agency comes up and says, I want to paint those collectors with, say, Go Dodgers for the series, you can monitor how much energy you use, and that's what you charge them in addition to the space. So you have blue and white for maybe.
But another good thing about monitoring the system, and especially having live monitoring, it will be the preventative maintenance that they can do. Absolutely. If they see something going down, if they see something not performing the way it's supposed to perform, they can intervene, that the contractor can intervene, they can have access to this information. A lot of our contractors, we know they monitor their systems very precisely, and they're aware of the system performance. So if they see something going on, before that leads up to a leak, before it leads up to something with a lot of damage, they can come in, fix it, no problem. So that's another aspect of monitoring that will be really important.
And the systems have alarms.
Yeah.
So you can get alarm on your phone. You can have it can come on your computer. You can have it texted or emailed to you. Please check your system.
Exactly.
Not the same.
I'm gonna speed it up a little bit because we want to leave some time just in case we have any questions at the end. So there are always other constraints that will affect the design of the system, the sizing of the system. For solar thermal, the one that you want to basically integrate into your building. We always look at how much space, we talked about it, how much space is available for the array. How much space is available for storage, we talked about these two. Another important factor is the primary hot water system configuration. How is the primary hot water system is set up, and how easy is it for the solar hot water system to tap into, so to speak? How we try to be as least invasive as possible, as far as integrating our systems into existing system, but the system also should allow for.
Yes, we don't want to interrupt pressure in the building or flow in the building at all. We also don't want to impact any of the high-end water heating systems that may have constraints. So we want to work with the manufacturers of those heating systems so we're not impacting the performance of their systems.
And another important factor is, what's the project motivation? Sometimes you have projects that they are basically mandated by the energy code that, okay, if you want to build this building here with this configuration that you have, you need to have this type of solar thermal system. So that explains the motivation of the project. Another factor is, like, some building owners, some developers want to go with green buildings, they want to go with net zero buildings, they're building in net zero communities, so they have to adhere to certain standards. Those are the motivations basically behind the project. And usually the least important factor that doesn't matter at all, we all know this, budget never matters. It's not important, never comes up, nobody cares about it. Why are we even discussing it? I don't know. But definitely the most important part is the budget available. Even if all the motivation is there and there is no budget, if you have all the roof in the world and all the space for the storage, they don't have the budget for it, and the system obviously can't go. And so a lot of times that's the main constraint. Keep in mind when designing the array, the number of collectors that can go into each bank, distance between the banks, the configuration of the array is always important. The array has the preferred array basically has to be facing due south if you're in the northern hemisphere, obviously, and then vice versa if you're going below the equator for a project. But you want to always face the sun as much as you can to maximize the performance of the system, basically. The systems are thermal systems. They're always under thermal expansion stresses, so that limits the number of collectors that can go into each bank. The pressure drops and the flow interruptions that you will get when the water goes into each of this bank is another factor that will dictate how many banks can be in each array and how they should be plumbed and how the piping between each bank should be set up, but there is a way for all of it, from a very small 1-2 collector jobs to all the way to solar thermal installations that involve probably thousands of collectors. There are ways to plumb them correctly, so they will be performing the way they're supposed to. It's just all of that has to be taken into account at the beginning. The more we take into account at the beginning of the project, the easier time we will have toward the end. So actually, I'm happy we made this timeline. We're right about this. So we have 10 minutes left until 12. There is a mark for us. So we're gonna open the discussion. I'm gonna stop sharing my screen, so everybody should be able to see us at this point. And I go over to the chat section and see. Okay, so we haven't. I don't see any questions being typed in the chat section at this point, and given the people who are actually attending, I'm pretty sure that a lot of people know what exactly we're talking about. So Bob, is there anything that you want to mention about what we talked about? Any important key factors that you want to cover before we sign off?
Well, what we are good at and what we strive is when someone comes to us with a project, sometimes they just put panels on a roof, just a drawing, and then sometimes they don't even include the solar tank. So we'll help them. We'll say, how is this going to go in? And they have no clue. So we have standard general drawings that we submit to the architects or engineers, whoever wants them. We help them. We don't direct them. We don't tell them what to do. We just help them to come up with a design that they feel comfortable with, and we review it and say, okay, wow, you got it right, yay. And then we said, well, by the way, what about the structure? And this might be the mechanical doing the job because it's assigned to him. What do you mean, the structure? Is it a tin roof or is it the superstructure? How are you going to mount the panels? We help with that. So sometimes the mechanical has to go to the building, the structural, and they have to have a conference and figure out that, they need larger trusses or beams or whatever to support it, and then to support the weight, and then they need the base structure, the frame or the base, like the chassis of a car, to hold all this stuff. And then from there we put the solar panels on. So we work with you on all that. Various buildings, if they're 15 stories up, they have different loading, wind loads. That's where structurals get involved. And if they're on the ground, if they're sheltered, if they're in high wind areas, which are getting more and more common, the Caribbean, obviously, we know what's happening there. The design requirements are different. They're stronger. They're more strict. You have to build structures or the racking that will, up to a specific wind loads that are usually specified by the jurisdiction. So we help with all that. And we review we make recommendations, we review the designs. Sometimes the plumbing size is oversized, sometimes it's undersized. We recommend that it be this way. And all those recommendations are based on, flow velocity charts so we're not over pumping the lines, and on head and flow numbers that we see from your drawings. So we're there to help.
So Bob, in the same sense that you're saying the design, we just had a question by Dale that what would be the advantage in the same design with the pumps? What are the advantages of using the multi-speed pump or variable speed pumps compared to on and off pumps in our designs that we use?
The advantage of a variable speed pump is that the solar thermal is working off a differential. So it's working off the temperature of the panels on the roof versus the tank temperature. So, excuse me, as the system goes through the day, there's variable temperatures on the roof. It goes up and down, and you could have clouds come over. And with a variable speed pump tied or integrated with a controller that's sending a signal to that pump, the pump will slow down or speed up depending on the temperature it sees. So example, if you have let's say you have clouds come over, the pump will slow down. If there's clouds that are on the fringe and are reflecting more energy into the panel, and that happens, we've had some interesting situations with that, the pump will speed up. It's all temperature driven. So the combination of the solar control that's monitoring those temperatures, feeding the signal to the variable speed pump, will maximize your efficiency. It'll keep your differentials within the design range we like, which doesn't always happen with an on-off pump. It's on. Example, if it's a prime example is in the morning. Sun comes up, the differentials met, the difference between the panels and the tank is met, an on-off pump comes on it. The water flows through it, cools down that roof sensor, and then, oh, the differentials met, the pump shuts off. Then the panels heat up again, and that cycle continues until the sun's high enough in the sky to allow the differential to maintain itself with a normal on-off. With a variable speed pump, that pump would be going slow, would start out at a slow RPM and flow, and then it would maximize itself to hot, if necessary, to its maximum flow capacity at the height of the day. So, and in that whole time, the pump is almost never off. It's always moving the fluid through, and you're gaining more energy that way. The more you can keeping the flow of energy moving through the system, the more efficient the system will be. And they use less overall energy than a standard on-off pump. So they're really the variable speed or high efficiency pumps. We're moving a lot of mechanical, industrial, and even commercial. Commercial projects are moving to variable speed, and then even now with the new codes in the multifamily recirculation area, the multi-speed pumps are being used to reduce the energy used and maximize the result to the end user. We don't want people without hot water building, or that's what you don't want. You want the system to flow perfectly. They all get hot water when they want it, and no one has a cold shower.
And Seth had a question for us. Can a variable speed pump be used to overcome the peak of drain back system and then throttle back to maintain flow?
It will. It can. Generally, with the drain back, most of the drain back installers out there, through experience, have found that this will work, and it'll vary the speed, which is good. But you always want the mechanical device you want on there is a throttling valve of some type on the return line. That allows for the cascading effect to be buffered, so to speak. It's throttled down, and then because the pump will have to get it up there and then drop it down. And once it drops down, then the variable speed will kind of kick in, but you still want a little back pressure on that gravity assisted water that's coming down. And that helps balance it all out. Once it's balanced, then the variable speed pump will vary the flow, and usually you have to set the minimums. You don't want, if it's too slow, then the pump will just reach like the top of the collector and stop. So you have that pump set for let's say 60 or 70% minimum up to 100%. But yes, it will manage those flows and drain back.
All right. I think that pretty much covers our presentation for the day. And I think we have one question from Seth about the fish in the background. The fish in the background actually wasn't caught by a colleague, it was caught by Ron.
Ron Mastro worked for Solar Ray Corporation for many years, and he started in Hawaii, and he caught that fish off of Hawaii. It was coming in to feed, but he had to have a place to put it, so
it ended up on our wall.
He came to work here for 10 or 12 years, and it's still there.
And that's why here at SunEarth we call our conference room the fish room. So when important delegates arrive at our building, we take them immediately to the fish room without it being fishy at all. But
sometimes we have sushi.
yes, we do. Thank you, Dale. I'm really glad that you enjoyed the presentation. Thank you so much for taking the time out of your busy schedules and spending this hour with us. We'll look forward to the next one. We really enjoy doing this, sharing this information with you all, and hope we'll see you on the ones that we have coming up next month.
Thank you.
Thank you.
Have a
Hi,
great
Mary
one.
still there?